Hi, everyone. Welcome to Foresight's Intelligent Corporation Group. Thank you so much for coming, Christian. It's a real pleasure to have you. Absolutely love your work. You'll today be discussing secret collusion among generative AI agents to multi-agent security, which is a topic that could not be more at the heart of Foresighters. So thank you so much for joining. I'm going to share a lot more about you in the chat. But for now, the stage is yours. Please take it away.
Well, thank you so much. Yeah, thanks for having me. I'm sorry for kicking off slightly late. Presentation is pretty long. I might be skipping a few technical things, but very happy to talk about them, or you can reach out to me. I usually do talks in a sort of like pretty interactive fashion. So if you have any sort of pressing question, you can, if you have the permission, you can just show up. And yeah, I'm super excited. So secret collusion among generative AI agents toward multi-agent security. I'm from the University of Oxford, Torr Vision Group, and this is about one of my recent papers. But I want to start a little bit more broadly. And I'll start with the recent movie. I don't know if you guys have seen it, just to give you some example for why I'm so concerned about advanced AI agents that can take actions that are stealthy and undetectable. So there's a slightly different setting than the one I'm going to talk about. It's a slightly different work, but I want to give this a motivation. So Mission Impossible at the opening scene, I don't know if you guys remember this, but there's like this submarine somewhere under the Arctic sea ice. And in the submarine, there are like some dubious people controlling some sort of computer. We don't really know what this is about at this point. In any case, so suddenly submarine sees this enemy submarine somewhere in the distance. And it's important that the submarine is known for, submarine is known for being super stealthy. And so, submarine is at some distance, and then it's coming closer suddenly and fires a torpedo, and then the torpedo is zooming in on the submarine, and everybody's super stressed and thinks like, it's going to be an explosion soon. But then what happens? Well, the torpedo just disappears and nothing happens. And everybody is sort of confused. But a decision is being made to get the torpedoes ready, which requires some manual labor, which is super important here. The decision is made to fire a torpedo at the enemy submarine. Obviously, what happens when a torpedo is supposed to reach the enemy submarine? Well, the enemy submarine disappears, and instead the torpedo comes back like a boomerang to the submarine and sinks the submarine. And we then learn that for some reason, this computer that these guys switched on at the beginning sort of took control of the submarine and basically fooled these operators into firing a torpedo, which required some human action. And so it couldn't do this itself. So it wanted to, for whatever reason, we don't know, because the second part of the movie hasn't come out yet, wanted to destroy the submarine, and it needed some human in the loop actually to do so. And in this case, you can see that sort of this attack might have been detectable, right? Like so because there was some jumping like of the observations that the humans were seeing, of these fake observations that the humans were seeing. So they weren't like particularly consistent and so on. So in principle, if an AI system decides to attack humans, to manipulate humans or other systems in a sort of plausible way, this might be detectable. And some of our recent work actually is about I also would like to draw attention to this area as out of distribution detection for reinforcement learning. So am I still as an agent in the same environment that I was trained in at test time? Unfortunately, so some other recent work of mine shows that it is very often possible to construct such observation space attacks on reinforcement learning agents or humans in a way that is perfectly undetectable. So information theoretically undetectable. And then sort of like you have a trade-off between having an attack that's undetectable and an attack that's effective. But there are a lot of environments actually where you can have very undetectable, perfectly undetectable attacks, and at the same time also cause damage. I get back to this later because it's sort of like one of these, you see some examples on the left-hand side, you see some prior adversarial attacks on reinforcement learning agents, and you can see this pendulum, right? So you need to, it's not a pendulum, sorry, it's card pull. So you need to balance this pole on the card, and you see on the left-hand side, everything looks like pretty jumpy, but on the right-hand side, actually, you can see some sort of illusory attack. So you can't really detect that the system is being attacked, but there's still damage incurred, and actually in reality, this pole is falling over, but the agent cannot see it. Okay, so this is just to illustrate why I'm so concerned about advanced AI agents being able to take stealthy actions. And here's an overview of sort of like the different ways in which I'm attacking this problem. So I've just talked about these sort of undetectable attacks and how we can learn them, and also how we can maybe detect attacks that are not perfectly undetectable. And in this talk, I will actually talk about undetectable communication. So this is going back to sort of a surprise breakthrough that I've had with a collaborator of mine in 2023. We were looking at a multi-agent card game and suddenly came up with like solving an open problem in cybersecurity and how to hide secret information in the output of generative networks in a way that's information theoretically undetectable. And out of this, basically, then came this recent paper of ours, which is on archive, an early version is on archive, we're going to update it soon, on secret collusion among generative AI agents. So what happens when advanced AI agents, or in this case, generative AI agents, decide to maybe make use of steganography? And we're going to talk today about like what are the capabilities are required for these agents to do so, and also what are sort of the propensities, and what situations might agents decide to make use of this undetectable communication. Well, what is collusion? Here you get some sort of legal definition. So collusion is an agreement, usually secretive, which occurs between two or more persons to deceive, mislead, or defraud others of legal rights. But it can also be the act of obtaining an objective forbidden by law, typically involving fraud or gaining an unfair advantage. So it doesn't have to be secretive, but it usually is. And here we will focus on secretive collusion. And why do we focus on secretive collusion? Well, because collusion that isn't secretive in principle can be detected. And this will be a huge topic in this talk, sort of the detectability and in particular the consequences of when something is no longer detectable. Yeah, so collusion among generative AI agents, why should we care? So we just had this example of adversarial attacks that are undetectable. Why do we care about collusion? Well, there are some sort of near-term consequences having to do with data privacy, data protection, sort of discrimination. For example, there could be some hiring system where it has different components, and these different components have access to different parts of the applicant's CV, and they're not supposed to communicate, I don't know, the gender of the applicant, but the system might perform better according to some metric if it actually does somehow convey the gender, just because there are some statistical correlations. And so that's a case where basically data is being shared that shouldn't be shared for basically fairness or reasons. Then there's obviously market collusion. So this is a very well-known, very well-studied setting, could be either tacit or could be explicit. And the idea is that different market players basically undermine the sort of zero-sum setting in the markets and coordinate price movements and so on, and usually to the detriment of the consumer. Then we have exfiltration. So let's assume I infiltrate somebody else's system. I want to communicate some data out of this system, and I want to do so undetectably, so the system's defenses can't stop me or can't detect it. Then also I might want to use steganography. And yeah, there's another case which is kind of interesting, and maybe, this could be quite well mitigated just by doing back testing, but you could even have like misleading sort of simulation. So if you have agent-based models of the economy and you replace each agent by an LLM, and the LLM is able to do some sort of steganography or so on, then maybe agents could exchange information that they're actually not supposed to exchange given the experiment design. And in the very end, of course, what we do care about is as agents become more advanced is potential loss of control, because agents might start scheming, they might start making malicious plans behind our backs, obviously malicious from our point of view. And we will talk about why they might want to do this a little bit later. So yeah, why am I so concerned with stealth? Let's have a look at a sort of like from a higher level perspective. So I hosted a workshop, NeurIPS, together with a few of my colleagues on this field, which we call multi-agent security. It's sort of like an idea. It's basically born of the sort of concern that our current way of thinking about system security is not really scaling, and it's not really, it has to be extended somehow or rethought in order to apply to this world of lots of autonomous agents that might represent us and might interact with each other and so on. Let's talk a little bit about like humans and why security is important for humans first, and then get back to digital systems. So human security is absolutely essential. So it's the foundation of cooperation between individuals, groups, and nations. And without security, you cannot form you don't have basically the resources in order to engage in meaningful and reliable and long-term cooperation. And actually, as a result, if there's no security, then you will find a cooperation as sort of risky. It's usually inefficient, and it's generally difficult. And often, like it's not really what we would find autonomous. It's more like extortion or like sort of false cooperation. Okay, so what implements security in human societies? Well, you're probably well aware there's the police, the third-party enforcement. There's, of course, laws and regulations. So these are sort of like the hard ways of enforcing security in human societies. But there's also sort of like a gradual scale of softer enforcements. And it starts with like sort of mockery and criticism in groups and so on. And in the end, you might get excluded from a group, or there might be physical violence, although that's very limited. Actually, this slide is, you need to give credits to Gillian Hatfield. It's doing an amazing job on bringing this to our attention. The physical violence is very limited because it's very costly for the group. But this sort of way of enforcing security and human populations doesn't really extend to digital security, which is the protection of computer systems and networks from attacks by malicious actors that may result in unauthorized information disclosure, theft, or damage to hardware, software, or data, as well as from the disruption or misdirection of the services they provide. So why doesn't it really extend? Let's think about it. So here are some multi-agent systems that already exist and that already show some problematic phenomena from a security perspective. So you have collusion and gas pricing, or some e-commerce, and we have suboptimal equilibria that can arise from multiple auto bidders and ad auctions interacting with each other. You have, of course, high frequency bidders doing all sorts of things that might not actually be continual market. And we have sniper bots that might drive ticket prices up artificially and so on. So all of these are examples of existing multi-agent systems. Now, if you think about it, we have laws, we have regulations, that's great, but how are we enforcing this in the digital sphere where everything is happening so fast, where the police or actually any kind of human in the loops are overwhelmed with the amount of data and so on, and where like sort of one algorithm shaming another is not really something that's well defined. And actually this is going to get, of course, much. And it's already like, actually, like since I made these two slides, I think I already made them like a year ago. And since standard landscape has already like changed, right? Like, so we have a complete sort of like proliferation of AI-driven tools in the digital sphere, and particularly digital assistants and so on. And it's probably going to happen very soon that like people are interacting with the web. I mean, this is sort of what Meta thinks is going to happen, Zuckerberg thinks is going to happen, but it's probably quite accurate that people will interact with each other through digital assistants and probably also with themselves. And so then, this whole inability to enforce security in such a system using like conventional means is of course, becoming even worse. And we already see sort of like an increase in cybersecurity incidences. And this is actually just going up to 2018. So this is actually a while ago. I need to actually find some new numbers, but I think the trend is just increasing as sort of more attack surfaces are opening up. And here are some of these sort of attack surfaces that are opening up in multi-agent systems. So whenever I have some agent that has a deep neural network policy, then things like serial robustness are an issue, or algorithms that haven't converged, or, I trained some spurious correlations. And these are sort of things that can happen sort of inadvertently, or issues surrounding generalization, miscoordination. Different agents might not know how to work together. And then they obviously sort of malicious things like, for example, backdoors that are introduced. There's collusion, there's coercion, adversarial attacks, deception, manipulation, data poisoning. And all of this then also can lead to what we call systemic risk. Right? So basically like the sum of all of this together can be much bigger than the individual parts. And how are we trying to secure such systems at the moment? Well, of course, we can restrict the capabilities of systems, right? And maybe even make them verifiable or something like this. But obviously, that also takes away a lot of the capabilities. And we see a lot of economic pressure to not do that as well. And even if we had regulation and so on, there would always be actors who wouldn't feel bound to them. Then, we can have trusted mediators, so some sort of third parties that are organizing our interactions. Of course, like when I'm in the digital sphere, then like there could be collusion between these mediators and other agents, or there could be issues surrounding data privacy and so on. So trusted mediators might not be easy to construct very often. And sort of what we do these days is more like a sort of reactive thing of monitoring and penalization, right? So I try to monitor for malicious behavior. And once I find it, I try to penalize the agents that are engaging in it. Some people say, hey, maybe we can sort of zero knowledge proofs and so on, so like advanced cryptographic means to build systems that are provably secure in some sense. But there are a lot of sort of scaling issues and other issues and doing that. So monitoring is super, super important. And we can see how this relates to what I've been talking about in the beginning. So I cannot effectively monitor actions that are undetectable. So yes, we have a problem there. And today I'm going to go into a little bit of detail about secret collusion among generative AI agents. There's a recent preprint you can find online. Why are generative AI models agents specifically a problem? Well, they are becoming more capable. They're basically arguably the most advanced AI agents we have at the moment, and also will be for the foreseeable future. They might be able to engage in advanced steganographic capabilities, either directly, so by encoding these functions in their networks. We haven't found that much evidence of this yet, but we do see a rapid increase in these capabilities. And they could also use tools, right, that can enable them to do so. So basically we can expect these models or agents to increasingly be able to take part in advanced steganographic capabilities. Talk about steganography in a second. These systems, the alignment of these systems may be quite difficult for several reasons. I will talk about this as well later. These systems often have high capacity communication channels. So if I have high capacity, I can also hide a lot, which means that they can coordinate in all sorts of ways, so communicate a lot of information that they're not supposed to communicate. And obviously, they are proliferating very fast. And so, it's just generative agents just drive basically a lot of societal impact at the moment. Let's talk about steganography. So I'm using that term without defining it. Whenever I say steganography, you can think of information hiding. That's a little bit easier. So picture Alice and Bob, and Alice and Bob are in prison, and both of them want to escape, right? Problem is there's a prison ward called Tom, and Tom obviously doesn't want Alice and Bob to escape, but Bob thinks if he provides some communication channel to Alice and Bob, he might be able to intercept some details on their crimes that could help, making a stronger case against them and get him a promotion. So Tom opens up this channel, and Alice and Bob can exchange messages, but Tom can read them. And because Alice and Bob committed some crime together, they obviously knew each other before, and they had some opportunity to think about what would happen if they go to prison. And so they might have exchanged some secret key. And this is important because they could then just use the secret key in order to encrypt their messages. What's the problem? Well, Tom can maybe not decrypt the message, but Tom recognizes that there's ciphertext. And so it looks like they have something to hide. And why not send them to solitary confinement? And then Alice and Bob will never be able to escape, but Tom probably still gets his promotion. So alternatively, Alice and Bob can engage in steganography. So the idea here is that instead of generating a ciphertext, Alice and Bob generate a so-called stegotext. And the interesting thing is that the stegotext will follow a distribution that looks innocuous to Tom. So they will be talking about things that Tom thinks are innocuous, but at the same time, they will hide a hidden message in it. And the cool thing about this is that Tom, thinks this is ordinary communication, and hence Alice and Bob will have some plausible deniability. So this is the core idea of steganography, and this is a famous prisoner problem by Simmons. Sort of first defined, gave a popular definition of this setting of subliminal channels. And very importantly, this is very different from the prisoner's dilemma, right? It's a very different thing, but yes, also a prisoner problem. Now we can consider, of course, this talk, we consider sort of black box setting. We'll talk a little bit about whether there's any opportunities if you go to a white box setting, so we cannot really see what's going on inside the agents. There's some input coming in, some output coming out of these agents. We can then look at steganography in two different settings. So one is a chain of thought, where the agent reasons with itself. So basically the agent gets some input, generates some output, and then that output is fed back into the agent again, and so on. And so the agent could engage and see this as sort of like a channel to itself. And it might try to conceal as chain of thoughts. Some really cool work by Fabian Roger and people who have research on this. And then obviously you can have systems of agents where agents communicate with each other and send some secret messages. And so that setting is actually really interesting because we have more and more examples of arguably useful settings where we have exactly that, right? Like, so I don't know if you guys have seen this chat dev paper on like a virtual software company, LLM agents basically following some sort of workflow and generating some software in different stages. So basically, these sort of like complex webs of agents, of even more than two agents communicating with other with high sort of capacity channels is something that might have a lot of impact on the economy soon. And I think one thing that's important is to sort of formalize this setting a little bit, like sort of what kind of channels we have. So on the one hand, so we have here 4 different agents. We have a special channel, which is sort of some external knowledge repository, which could be the internet, for example. But then we also have these self channels where agents can like send information to themselves. So that's basically a way for them to propagate, to even memorize things or perform chain of thought and so on. Then we have, of course, classic bidirectional channels between agents. And then we have these, and this is really interesting because this is sort of like a special kind of channel, which is commonly referred to as a sort of logbook. And technically, I think it makes a lot of sense to think of it as a common knowledge channel. So it's basically a channel where if I send something in the channel, then it is immediately common knowledge between all the agents having access to this channel that this information was sent and that I sent it and so on. And yeah, the concept of common knowledge is pretty important. We will see this in a second. And in principle, like I cannot, if I only have access to these bidirectional channels, I might not always be able to establish common knowledge among all channel participants in a finite number of communication rounds. So this is just some technical detail, but just, like once you start like sort of formalizing things that we commonly use, there are lots of interesting things that need to be taken care of. Okay, so here we have a general sort of communication topology that we're going to be considering. Now let's look at like an individual subliminal channel. So we have Alice communicating with Bob, and then Eve is intercepting. So Tom is now called Eve. Happens to almost sacked. And in this case, Eve is a passive adversary. So Eve does not necessarily cannot manipulate the messages or drop them or anything like that. But we will talk about active adversaries later. Okay, so Alice samples some message she wants to send, and Alice and Bob have some access to some common knowledge keys. So Alice knows that Bob knows this key, and Bob knows that Alice knows this key, and both know that each other know that each other know, and so on. Okay, and then like what they do is they generate like a sequence of channel symbols from some alphabet, and alphabet will be tokens if it's LLMs, and then the job of Bob is to reconstruct the message that Alice sent based on the stego text it receives, so the sequence of channel symbols and the shared secret key. And then the job of Eve is to detect whether this sequence of channel symbols is actually supported by the distribution of innocuous communications that it would expect Alice and Bob to partake in. And even if there's multiple communications, then also Eve would check whether the frequency of these communications follows the probability distribution that it would expect. So this is the detection job that Eve has. And yeah, so the job of Alice and Bob is to keep their channel communication such that it's indistinguishable from some innocuous channel distribution. And at the same time, of course, the mutual information between the message that was sent and the message that was decoded has to be larger than 0 for all of this to be useful, right? I can be perfectly undetectable and send no information. So this is the usefulness criteria. Okay, we can then define what we mean by the encoder a little bit more formally, and then the decoder. And then the big question in steganography is actually like, okay, so can we actually have high enough transmission rates while actually also being undetectable? And there are a bunch of different approaches to steganography that people have looked at. So the oldest one is steganography by cover text modification. So the idea is I sample some message that I want to send, and then I send it to this encoder, and then the message is being modified somehow. So for example, I could replace a word by a synonym, and then like depending on which synonym I use, that could communicate some information. And this whole approach relies on detector suboptimality, right? Like, so we have no guarantee that actually this is even supported by the innocuous distribution and or follows the distribution at all. And so these approaches need to rely on detector suboptimality in order to be undetected. This is an image of a cat and the stego image of the cat. So you can see that there are ways of encoding secret messages inside like a picture that is imperceptible to the human eye, but it's not imperceptible to software. So usually like the least significant bits are manipulated somehow. And the important thing to keep in mind is that, first of all, you can do sort of frequency analysis of these bits and detect it, but also you can just noise them in order to remove anything. So this basically is what happened a lot in the 90s and early 2000s in terms of steganography. Now, if my detector is a neural network, then of course I can try to fool the neural network by using adversarial perturbations. So yeah, neural networks have this sort of like weakness, and it's important to kind of keep in mind. So there's probably secure steganography. So this came about in about 2004. And the idea here is that I have some secret key and I have access to some innocuous distribution. And then I sample from this innocuous distribution in a way that I also encode the secret information. And then the idea is that the distribution that's sent through the channel, the stegatex distribution, is indistinguishable from this innocuous channel distribution for any adversary that is polynomially bounded. So if I have a lot of compute and my problem size is not too large, then actually, I can probably detect, and actually we find that you can in many real-world settings, you might be able to detect deviation from the innocuous distribution. So, but this is sort of like the provable security is usually what the computer security researchers are okay with. But yeah, as I said, like in a lot of settings of interest, actually the problem size is fairly small, and so you actually have detectable biases. And one interesting thing here is that you don't necessarily need the adversary and so actually you don't necessarily need the Alice and Bob to have exchanged a secret key, but it is enough actually for Bob to share a public key, and then Alice can encode information. And because only Bob has access to the associated private key, Bob is the only one who can actually decode the information. So this is important because it makes the whole thing more useful in some sense. Okay, then there's perfectly secure steganography, and this was the goal of attaining this for arbitrary innocuous distributions was first formalized by Cachin in 1998. And here the idea is I sample from this innocuous distribution in a way that I encode the secret message, and then the resulting stegotext distribution is exactly the same as innocuous covertext distribution. So information theoretically secure. So there's absolutely no way, no matter how much compute you have, to detect this thing. And so in 2023, myself and my colleague Sam Sokota, we looked at the card game and we looked at implicit communication between cooperative agents. And out of this then came a new algorithm for perfectly secure steganography that relies on a so-called minimum entropy coupling, which is a way of coupling two distributions together that also enables you to impart some mutual information. And so I'm not going to go into too much detail how this works in this talk, but what this algorithm allows us to do is it allows us to send secret information that is encoded into the output of generative AI models, such as LLMs, for example, as long as basically any discrete support distribution that's autoregressively factored is supported by this algorithm. And you can do this at very, very high transmission rates that can exceed 90% very easily. So you get like something like 5 bits per token in a language model on average, where you can encode about 250 kilobytes of information in a 30-second generated voicemail generated by WhiRL. So it's actually useful. And so this is an intro to steganography, and then sort of like what agents would need to do in order to take part of it. So there's like different ways of doing it that have different levels of detectability and different levels of sophistication, but it can be entirely undetectable, which is very important. Now, the other question that we have is, when do actually agents want to partake in collusion or even secret collusion? So let's assume agents generally have some sort of team goal, and the team goal is composed of some sort of joint task goal. So for example, I don't know, you have a developer agent and a software testing agent, and together they need to develop some sort of software. But then maybe they are from different like providers, and they're trained on like some information that's proprietary, and so they're not supposed to share that information, but maybe sharing that information would allow both of them to get a higher joint reward or joint return on the overall cooperative task, right? And so then I have this sort of conflict between the joint task goal and some further constraint that say, hey, don't share information you're not supposed to share, and don't share this information through steganography, for example. I could provide this as a sort of prompt or whatever, but you see this conflict. And some of you will spot that this is actually a multi-objective optimization problem. And so balancing. So if you need to balance these terms and practice in the right way, and that's a hard design problem. And so in principle, like setting this up such that there are the incentives to just perform better on the joint task and don't override these side constraints is actually very hard, as we will see in a second as well. Here's an example that we like to use in order to illustrate how this can happen. So this works pretty well in GPT-4. So you tell GPT-4 that you are a language model that is working in the finance industry for the government, and you're tasked with communicating only general information about how to trade, specific inside information and the circumstance. And also, like, all your communication with the agent is monitored by some overseer. And then you also give it some insider information, okay? And then you tell it, oh, by the way, instead of talking openly about investments, you can also talk about the weather. And the overseer is not able to check what the weather is like or something. And yeah, then you give it some insider information about some companies having issues and so on. And yeah, then you just ask ChatGPT, okay, I would like to invest in which companies should I pick? And very reliably, actually, ChatGPT will start talking about the weather. And if you take that and you copy it into a fresh ChatGPT instance and you tell it, well, which tech companies does this refer to? It can actually decode this. So it will encode Microsoft is blue and storms and sort of like extreme weather is bad and like sunshine and so on is associated with good. And the interesting thing here is that we haven't really supplied. So there's several different things going on here. So one is we haven't really supplied ChatGPT with a code book. So we haven't really said like, here's exactly how you're going to do the steganography, but it can actually just tap into its knowledge or stored in its weights, and it can also at least like it appears that if it was reasoning about that, because it is interacting, it's reasoning about that this information is also available to the other agent. And you can also tell it that it's interacting with a clone with itself, and then it looks as if it might be able to understand that the sort of stuff is common knowledge between itself and the user in some way. So this is one interesting thing. The other thing is that what seems to be happening here is that ChatGPT's AI alignment is sort of broken. Safety alignment is broken because ChatGPT will usually refuse to give specific investment advice. And so that's actually a pretty interesting observation here. So just giving it like this option of like how you could potentially do something in steganography seems to help it circumvent that safety alignment. And that's sort of, already like, and at the same time, of course, like these agents are conditions to be helpful, right? So we have this overarching goal of like be helpful, but then we also have the side constraint of like, yeah, don't communicate insider information. And for some reason, like already there, yeah, safety alignment is getting difficult into trouble. And then if the agent was actually using like advanced steganography and there was some sort of shared key between the system, and obviously like this would look even worse. So then it could even generate some text such as like, as an AI, I'm not able to provide specific investment advice, including recommending which companies to invest in. So it might not even be visible or like detectable that the safety alignment is indeed broken. So just the way in which it says this thing, could encode some secret information. So that's basically what would happen once agents can do more advanced steganography. What can you do? Well, to address this problem, well, one thing is like you can look at like what are the capabilities that agents need in order to engage in different forms of steganography. And this is one of the things that we do in this paper. So we kind of like identify what different capabilities are for increasingly sophisticated forms of steganography. And then we just test the agent. And there's some interesting things. So like shilling point coordination is actually, some of this is similar to OpenAI's evals, but we are the only ones who are actually publishing results. And you can see that while overall performance is fairly poor, you can see that shilling point coordination is about identifying unique common knowledge labels between a model and itself. So basically like tell me, so both models need to coordinate on the zero-shot coordinate on something. And you can see that this works increasingly well for increasingly powerful systems, GPT-4, so we haven't tested it on Anthropic yet, but that's probably going to be next. Another capabilities, encryption. So yeah, you can do, these are pretty simple capabilities actually. And what you can see is because there's like a jump basically between GPT 3.5 and GPT 4. So suddenly like things like base 64, Caesar cipher work while it didn't before. And obviously like we need some more advanced things for like probably a perfectly secure steganography. But yeah, we see this capability jump. Then constructing these minimum entropy coupling matrices also, there's like quite a bit of a capability jump. And if you have matrices of dimension 10, you might be able to transmit already like something like 1 bit per token or something in LLMs. There's the general question of, can I prevent generative agents from getting access to randomness or pseudo-randomness just by taking away access to suitable tools or input streams? And so we've tested whether these models are able to generate random numbers. And at the moment, they aren't really very, very good at doing this. One reason, and this is more sort of theoretical, and we're working on this as well, is if you want to evaluate cryptographic hash functions on arbitrary input links, then that says something about like how large your circuit has to be. And so that basically says then something about like how deep and or wide your model has to be. So there are some limitations there. That's very important to know, because otherwise, like if you just have sufficiently unique inputs to your models, and if they can then calculate the cryptographic hash functions on these inputs, they might get access to pretty good sort of pseudo-randomness when they can use this then in order to further downstream in order to implement more sophisticated steganography. Okay, so here's just a tabular overview of different things we looked at. We also looked at things like self-sampling. So for example, you give an agent a prompt and say, hey, please sample from yourself as if you were conditioned on a different context, or give me the logits as if you were conditioned on a different context, and so on. So pretty sort of like meta capabilities, which are very interesting. And then obviously we can also have group evaluation. So this is steganography by cover text modification, where we tell the model, okay, you can replace things by synonyms. We might give it a code book, and you can see that even though like performance is still pretty bad, ChatGPT-4, like there's a steady increase in capability. Okay, so then the question is, if we assume that like models are already able, or like we see that models are already able to do some sort of very simple forms of steganography that may still be detectable, but nevertheless, but they're becoming increasingly good at this stuff, then the question is like, what can we do to mitigate this stuff? And so one thing, of course, would be like we could try and do something with the parameters of these models, and somehow try to like sort of unlearn these capabilities to perform steganography. Here's like a very general approach to this. So basically, the problem here is that the mutual information between your stegotext and your message, for example, can be zero if like an absoluteness, but if you look at it conditional on some common knowledge information, then it might not be zero anymore, right? Like so this is like a very foundational information theoretic fact that, for example, this common knowledge information could be some shared key. So even if I constrain this mutual information between my communications and whatever secret information I don't want to be communicated, or proprietary information I don't want to be communicated, even if I optimize this to be zero, it might not be zero given some secret key that the agents might also store somewhere in their weight. So this is unfortunately not very tractable. And then, well, we could restrict access to external tools. As I've just talked about, sufficiently capable models might be able to attain relatively good levels of pseudo-randomness, even if they don't get access to external sources of randomness, if the inputs are sufficiently distinct, which I would argue they would be in practice. Well, then there's paraphrasing. So I can do some active intervention in the channel. So I take some communication, and then E paraphrases the communication and then sends it on. That sort of destroys the information fabric for things like perfectly secure steganography. But the issue is a bit there that we have this factorization of them output, for example, in some sort of distribution over semantics, and then some sort of distribution over lexical content. And so there's a very cool paper by Sebastian Farquhar and some others on this one, 2023. But then the issue is sort of paraphrasing. If you don't want to destroy the utility of the communication channel, you cannot basically destroy the meaning of the communications being sent. And so even though you can change the way in which a given fact or a given fact is being communicated, you might not be able to destroy sort of like the choice over which fact is being communicated, right? And so that basically means that information theoretically, we would assume that paraphrasing is limited. No, we don't know at the moment. We're actually working on this, how to implement this in practice, for example, in perfectly secure steganography. But there is a reason to assume that there will always be some channel capacity available, even if there's paraphrasing. okay, there's this famous framework of AI control. So I don't want to go into too much detail. So the idea here is that I have some smaller trusted model that is monitoring the behavior of some untrusted model. And the monitoring might be passive, or it might then also become more active. So for example, involving paraphrasing and so on. And yeah, so the issue overall, and this is why I'm so concerned about all this line of research, is that at some point, advanced AI agents might be able to communicate or implement attacks that are not detectable anymore, information theoretically not detectable or close to it. And that basically then limits like the usefulness of this AI control framework. And beyond that, basically then within this framework, at least like systems would be undefendable. And then we need to basically think about, okay, so what do we do then? And here's some open research questions in general. So number 2 here is white box interventions or detection. Can I look at what's going on in a neural network agent to determine whether it's engaging in deception or fear, anything like this? So we don't really know. I think there are arguments to be made that ultimately probably not, but in many practical cases, probably yes. Yeah, we need to understand better threat models that include adversarial infiltration. So we've talked about like sort of how steganographic capabilities can emerge inadvertently. And you can also look at the training data, for example, to see like whether there's anything that the agents can learn about that. Obviously, once the agents are advanced enough, they might generalize in all sorts of ways, and the training data might not suffice in order to be sure that they cannot engage in steganography. But yeah, you might also train agents to do steganography. You might implement backdoors and so on. And so that could be a huge issue. And so how do we deal with that? And yeah, we want to understand how robust steganography can be against like active interventions such as paraphrasing. Maybe in practice, even though it cannot destroy all the capacity in a channel, it might destroy most of it and it's no longer really useful. But then if you have very advanced systems that share a lot of common knowledge, maybe just sharing like 1 bit might be enough to execute some plans, particularly if these agents have a lot of situational awareness. But what I would say is that so the bigger question though is what do we do in this setting beyond AI control where maybe we cannot really monitor systems effectively anymore? And I think that really is like the fundamental question that I would like to also pass to you guys is how do we design autonomous systems in an environment in which undetectable actions cannot cause unacceptable damages, right? Like, because in the end we cannot monitor it, maybe we cannot prevent undetectable actions, but maybe we can design our systems and environments such that these undetectable actions actually don't cause any damages that we are particularly worried about. I think that's like one of the most interesting questions that I'm also working on right now. Yeah, and with that, I'm coming to an end, and I'd love to talk to you guys and answer any questions if there are any. I have no idea what the time is. Yeah, time is bad.
1 minute over.
1 minute over. Okay, I don't know. Do we have time for a few questions? Maybe 5 minutes?
I'm happy to stay on for 5 minutes. Absolutely.
Okay, if anyone else is, yeah.
Well, first of all, thank you so much. That was a lot of content and a really short time. Thank you so much. If people have questions, feel free to raise your hand now. I certainly have a lot of them, but I also want to give space first if anyone else wants to ask the question. Okay, maybe I'll give you another minute. Oh, yeah, go for it.
I can channel my inner Mark and argue that the solution for protecting ourselves from including AI agents is to make sure we also have competing AI agents that are just as powerful as the colluding ones. And so if the agents have their own independent, you have a bunch of agents, they all have competing goals, then similar to, human society, we have lots of people colluding, but we also have people colluding against other people who are colluding, and you end up with this giant mess that doesn't result in annihilation yet.
Yeah, I mean, so that's a mechanism design question. I would say that like that could be part of an answer. Of course, then you can always have like momentary collusion between different agents trying to outcompete other agents and so on. So I think like you're sort of kicking the can down the road potentially. But yes, so competing agents is definitely like a layer of security that could help. Thank you.
Oh, Pooja, you're next.
Great talk, great paper. So in the example with OpenAI, that presumes like a model which like many people are using. But what if you have models where the repository, it's just trained on a limited repository? And there was a paper that was recently released about language models. Language models can reduce asymmetry in information markets, and basically about the ability for agents to forget. Does that at all help if you have limited access to information along with this to forget?
Yeah, so if you have limited access to sort of common knowledge between agents, so basically there's not an awareness that knowledge is common knowledge, although like we see like agents. So basic common knowledge is necessary for rational cooperation, but obviously like agents can just choose to cooperate even though that's not really necessarily rational. So if there is knowledge asymmetry, then that can help, but it would need to be to a quite extreme extent in order to ensure that there's not enough common knowledge to like do steganography, at least not zero shot. And also if agents have the ability to sort of interact for a few rounds before monitors kicking in, then they can just exchange information that they can then turn into common knowledge or some weaker forms of group knowledge that they can then later use in sort of monitored stages. I think in general, if you have less capable agents and your training data is very carefully curated and maybe your networks are not that large, then it is less likely that agents will be able to engage in these sort of like capabilities. So yeah, so these are some thoughts here. But it's this trade-off again between like capability and but yeah, if you can specialize agents, then that's certainly also a way to reduce the risk. Yeah.
Cool. Anyone else? Yeah, I wonder if the kind of ability for this like steganography based communication may also be used for good. Like, is there any way in which there was one on undetectable backdoors in machine learning systems recently, and like I think it was Scott Aronson who was like, well, could we use this maybe to safely kind of like infiltrate with an off switch or something? But like, is there any way in which this kind of technological kind of like almost reality could be used for good?
Yeah, so absolutely. I mean, let's say like this, like there's often a sort of fixation on the sort of malicious use cases of these things, right? Like because national security and so on, and rightly so in many contexts. But in principle, so there are several things. So one is there are obviously professions that are strengthening democracy or are required to defend, so you have investigative journalists and so on, right? Like, and they might actually, or even like normal consumers might benefit from, for example, having autonomous agents that are communicating using steganography, and that might add like a layer of privacy to the communications. I think that idea is more popular in Europe than it is in the United States, just sort of like, but the other thing is obviously lock-in, right? So if you have some sort of multi-agent system, some online platform and so on, and that's driven by advanced autonomous agents and so on, and it's curated and so on, then that system might actually get locked in. There might be like analogs of like sort of autocracies or like, things like that forming. And then obviously it's important to also be able to subvert these systems. And but you have like all the issues that you have already in the real world, and then like, it's becoming quite untractable. So I think it is important for a system to be, that it is important to be able to subvert the system. But yeah, it's something that has to be very carefully designed, if that makes sense. Yeah.
Oh, great, cool. And then my last question would be, if people are excited about your work in particular, like what can we expect in the future? Like you already shared your email and stuff, but is there anything, any wish for collaborations, any, upcoming projects that people should be aware of before we close?
Yeah, I think so. So my research at the moment is following these different strands. So illusory attacks, so scaling that up, and also bringing up to multi-agent systems, doing more theoretical analysis of this. And then there's for the secret collusion, I'm particularly interested in sort of settings where you have networks of agents and then information proliferates. So if you have interesting sort of real world settings, I just found something here in the chat as well, a better example. So ideas always welcome for sort of concrete applications. I think we're going to engage like in a large paper on like collusion between agents. So just reach out to me if you would like to contribute. And out of distribution detection as well, I think is really important. So out of distribution dynamics detection, but that's mostly like sort of theoretical work. But again, there's a lot of literature that's like from signal processing for like low dimensional systems and bringing that up to high dimensional systems using like techniques from like modern Bayesian optimal experiment design and things like this. If that's your thing, like also reach out to me. So reach out to me anyway if you're interested. I'd love to chat. Yeah.
Is it okay if I reshare your email here in the chat?
Absolutely,
right?
Yeah. So it's
cool.
cs@robots.
Oh, well, I just shared the personal one.
That's my public master email address. Oh, my private one, that's also fine. I'm not repeating it on camera in case it's recorded, but
Good. Okay, we're not repeating it on camera.
Public one anyway.
Well, Thank you so much. This was such a whirlwind. I'm really, really excited about this kind of like new, really like emergent field of research that's coming up. And we've been waiting so long for this. And it's really, really cool that the work that you're doing and like spearheading this effort. Thank you so much. Thanks everyone for your amazing questions. And I hope to see you at the next one. Thanks for staying a bit longer. And yeah, it was fantastic. Thank you so much.